Hello, am I audible? So can someone let me know if I'm audible in the chat? Okay. Okay, so let's begin. Welcome to week 4 of the problem solving sessions of this NPTEL course Advanced Power Electronics and Control, which is taught by Professor Avik Bhattacharya. My name is Soleh Khan and I'm a PhD student at IIT Delhi, and I'll be conducting these problem solving sessions on Mondays from 6 to 8 p.m. So I'll start with a summary of the content that was taught in this week, and then we'll solve some problems based on that content. So in the week 4, the three main topics were taught. The first is power PWM rectifiers. This was continued from the last week. And then power factor correction techniques, and lastly, non-isolated DC-DC converters. So let me begin with non-isolated DC-DC converters. So the three basic converter structures uh, that we'll be studying are the buck converter, the boost converter, and the buck boost converter. So they all have an input DC and an output DC, and the load can be resistive load or some other kind of load. So what you should notice here is that all three of them have two complementary switches. So they have two switches that are turned on and off in a complementary fashion. What does that mean? That means if one switch is on, the other must be off. And if the other is on, the first one must be off. That is what I mean by complementary switches. And that is necessary because if both of them are on at a time, then something will get shorted. For example, in the buck converter that is on the left, if both of these switches are on, then you can understand that the input voltage will get shorted. So that will draw a large current through the devices until they just basically will get damaged. So that is why if we turn on the top switch, the other bottom switch must be off. And similarly, if the bottom switch is on, the top one must be off. But it is possible that both of them can be off. So that is what happens in discontinuous conduction mode. But both of them cannot be on at the same time. And that is the case for all three of these converters. So similarly for boost converter, if you see both of these switches are on, then the output voltage will be shorted. So the output voltage we get zero. And if we have a capacitor here, and so the output voltage will stay, it will retain voltage. So until that time, there is some voltage, and both of these switches are on, they will draw a lot of current. Similarly, if in buck boost converter, both of these switches are on, they basically V in plus V out gets shorted. So both these switches cannot be on at the same time. And at least one of these switches has to be a controlled switch. That means we should be able to turn it on based on uh, our desire. When we want it to be turned on, we should be able to turn it on. So it should not, both of them cannot be diodes because diode is an uncontrolled switch. One of them has to be a controlled switch like a thyristor or a MOSFET or an IGBT or a BJT. So one of them has to be controlled, and uh, it is not that any of them can be controlled, but specifically one particular one has to be controlled. For example, in the buck case, the the top switch, which is connected to input voltage, that one has to be a controlled switch. In the case of a boost converter, uh, the switch that is connected between the inductor and the ground or the negative of the output voltage, that one has to be a controlled switch. Similarly, in the buck boost case, the switch that is connected to the input voltage, that one has to be the control switch. So, so that is about the switches. And another thing that you can see in all these three converters is that they have one inductor and one capacitor. Even though the capacitor is not really necessary, some converters you will see some choppers in these structures they will not have the capacitor. And though so basically these inductor and capacitors are the filters. You can do without them. For example, the buck converter, you can have a buck converter without the inductor and the capacitor, but then you will not get a constant voltage at the output. You will get some pulses of V in and zero. So the inductor and capacitor are basically filters. And for at least for boost case, you have to have this inductor or you have to have a current source from the input side instead. So here I have shown a voltage source plus an inductor. If you have a current source, then so this inductor basically means it is a current source. It basically means that the current from the input, it will not change suddenly. So you have to have this inductor or a current source here. And so another interesting thing that you can notice among these three converters is, so I have uh, highlighted the two switches and the inductor in a little box in all these three converters. And if you notice, the other than this box, the other converter, the input voltage, the output capacitor, and the load, they're the same in all these three converters. And this dashed box, what is happening is it is just rotating. So in the buck converter, we have switch connected to the input, inductor connected to the output, and another switch connected to the ground. In the boost case, this has been rotated. So this inductor has come to the input side, and the switch has gone to the ground side, and another switch has gone to the output side. And similarly for buck boost case, there is another rotation. So the inductor is on the ground side, one switch is on the input side, and another switch is on the output side. So this is something called what is called a three-terminal cell. So if you notice that this box has three terminals, one on the left, one on the right, and one on the bottom. And these three terminals are just being interchanged for buck converter, boost converter, and buck boost converter. So the point here is that uh, these converters are all basically made of the same components, just connected in a different fashion. So there are different control strategies on how we get the desired voltage from these converters. The first one is a current limit control, which I will talk about later in the problem solving. So right now I will just talk about the time ratio control. So the first type of time ratio control is a constant frequency control. So so constant frequency means, so like I said, these switches, the two switches that we have, they are operated in a complementary fashion. So if I know when one of the switch is on and when that one is off, I can know when the other one is on and off as well. So for example, here in the top diagram, I've shown T on and T off. It's a pulse. These are pulses with on time and off time. So this is the on time and off time of one of the switches, and the other switch will just be the complementary of this. When this switch is on, the other switch will be off, and vice versa. So here I have shown that for some duration the switch is on, and another duration the switch is off, and then again the same thing is happening. And what is interesting to know here is that so this is something that is called duty ratio. The duty ratio is the ratio of the on time divided by the T on plus T off. That is the duty ratio. And duty ratio is the controlling function of these converters. So if I increase or decrease the duty ratio, my output voltage and my inductor current will change depending on the duty ratio. So one of the ways to change this duty ratio is to just increase or decrease the T on while keeping the overall time constant. T on plus T off is constant. If T on plus T off is constant and I increase T on, I will be basically increasing the duty ratio, which I have shown here. So in the bottom diagram, T on has been increased, but T on plus T off, this total time is the same. So that is why it is called constant frequency, because this is the switching frequency, how fast or how slow the switch is turning on and off. That is the switching frequency. And in this case, the switching frequency is constant. So after T on plus T off, after in all these cases, after T on plus T off, the switch is turning on again and again. So that is why the switching frequency is constant. And by changing the T on and T off times, I will be able to change the duty ratio. So that is one way to control these DC-DC converters, non-isolated DC-DC converters. Another way is to have a variable frequency control. So for example, in this case, I have shown T on the time that is the switch is on, I have kept constant. But now if I want to increase the duty ratio by, and the condition is that I want to keep T on as constant, the way I can do it is decrease by decreasing T off. And when I decrease T off while keeping T on constant, I am changing the switching frequency. I'm increasing the switching frequency. So if you see in the bottom diagram on the right, T off is smaller. So that is why the switching frequency is increased. So in order to increase the duty ratio, I have to increase the switching frequency as well. So that is the difference between these two control strategies. So in constant frequency control, if we want different voltages, we can get these different voltages at the same switching frequency. But in variable frequency control, if we want different voltages at the output, we will have to change the switching frequency as well. So that has some advantages and some disadvantages as well. But here we will mostly talk about the constant frequency control. So we will have a constant switching frequency, and in order to change the duty ratio, we will increase or decrease the T on time. So this was about the control strategies. Now something that you will hear often is CCM and DCM. CCM means continuous conduction mode and DCM is discontinuous conduction mode. So for example, on the left, I have shown an example of a continuous conduction mode. So the inductor current in this case is always uh, positive. Okay, so Sivanesan is asking about variable frequency. So I was saying that in DC-DC converters, one of the control variable that we have is the duty ratio. And the duty ratio is defined by the time T on divided by the time T on plus T off, which is basically the switching time, the inverse of the switching frequency. So this duty ratio is the control variable. By changing this duty ratio, we can change the voltages and currents in the converter. Now, there are different ways of changing this duty ratio. One way is to have the switching frequency, overall switching frequency constant. That means we will have T on plus T off as constant. And then by changing the T on time, we can change the duty ratio. So that is constant frequency control. Now, if we want to keep T on time as constant, we don't want to change the time T on. So like here I have shown this time T on from top to bottom, it is the same. But I want to increase the duty ratio. So I can do that by decreasing the T off time. And when I decrease the T off time and keep the T on time constant, I am basically increasing the switching frequency. because as you can see in the bottom case, the switching is turning. You can to see the switching frequency, you just uh, see the rising edge of uh, this waveform. The rising edge is coming closer from the compared to the top waveform. So that means the switching frequency is increasing, because the switching frequency is basically the time between any two rising edges or any two falling edges. And you can see that in the bottom case, if I want to increase the duty ratio while keeping T on time as constant, I will basically have to increase the switching frequency. So this is one way to have variable frequency control, by having a constant T on. Another way can be by having a constant T off. And in that case, we will have a constant T off, but T on time will change. And then the switching frequency will also change. Okay, so that was about constant frequency control and variable frequency control. Now I was talking about continuous conduction mode and discontinuous conduction mode. A simple way to understand this is, if the inductor current uh, is always positive, then we can say that it is continuous conduction mode. But if the inductor current at some time it goes to zero, then the then we call it discontinuous conduction mode. So that is a simple way to understanding, even though it is not, it is simplifying some things, but at the basic level, this is how we will define discontinuous conduction mode. And this discontinuous conduction mode arises because if the switches cannot conduct bidirectional current. So if we have switches that are able, both the devices, so I mentioned in buck converter, boost converter, and buck boost converter, the conventional buck boost converter, they have two devices, two switches. If both of these switches are not bidirectional switches, that means they cannot conduct current in both directions, from one terminal to other or the other terminal to the first terminal. If they are not bidirectional current devices, then discontinuous conduction mode is possible. If, however, they both are bidirectional uh, con- uh, if they both have bidirectional current capability, then we will not have discontinuous conduction mode. Even if our average current drops, we will still have continuous conduction mode. The current will just go negative, and it will continue just like it will still be a sawtooth or a triangular wave, but it will go negative in that case. But because if we don't have devices that are able to conduct negative current, in that case, we will, if the average current falls, then we can have discontinuous conduction mode. And in discontinuous conduction mode, the inductor current basically goes to zero and stays zero for some time. So in now let's talk about steady state analysis. What steady state analysis, uh, in its most basic form, what we want to do is we want to find out what is what will be our output voltage as a function of the duty ratio, and what will be the average inductor current as a function of the duty ratio. So these two things we want to find out uh, at the basic level, and later on we can find out some other things as well. But in steady state, and we want to find out what the average output voltage, average inductor current will be in steady state. What steady state means is that our currents and voltages are periodic at the switching frequency. For example, here I've shown the inductor current, and it is in CCM, continuous conduction mode. And you can see that so if I take any point, so let's say if I take the 0 point on the time axis, and after a switching frequency period, so after a period of ts seconds, my inductor current reaches to the same point as it had started. So that means this inductor current is periodic at at the switching frequency. So I can take any point of time. So if I take this peak current, and if I add ts time to the time axis If I go forward by Ts time, I will see I will again reach to the same point. So that is what I mean by steady state. So if a circuit has reached steady state, that means after the switching frequency, it will take the same value. So in that case, so this is for DC-DC converters. So in a DC-AC converter, it will not go to the same point. It will go to some other point. But for DC-DC converters in steady state, we will after every Ts seconds we will reach to the same point, and that will help us in analyzing these converters. So, for example, again I will use the inductor voltage equation and the capacitor equation, which is for inductors it is L di dt is equal to the voltage across the inductor. Now I can write this in terms of the integral of the voltage across the integral of the across the inductor, and then I can basically write that 1 by L in integral of the inductor voltage from 0 to this time Ts, it will be equal to the inductor current at time Ts minus the inductor current at 0 time. So just from this rearrange, if I rearrange this and I integrate it, I will get this equation. And at steady state, the condition is that the inductor current at Ts will be same as inductor current at time 0, because the inductor current is periodic at the switching frequency. So the inductor current at time Ts, like here, it will be the same as the inductor current at time 0. So that means this integral will be 0. So this is something that is called the volt second balance of the inductor. So if you see, this is voltage and has to be multiplied by some time, and overall the integral of the voltage across the inductor, it will have to be 0, because the inductor current reaches the same point after time Ts. So similarly for the capacitor, we can see if I write this differential equation in terms of an integral equation, I can basically see the integral of the current through the capacitor from 0 to the Ts time, it has to be 0. Because again, just like the inductor current, I can say that the capacitor voltage has to be periodic. So the capacitor voltage at time Ts will be equal to the capacitor voltage at time 0. So if that is the case, then this integral will be 0. So this is called the capacitor charge balance, because uh, the capacitor current the time it will give us the charge in the capacitor. So when we do this steady state analysis, as I will show for the buck boost converter, we will make some assumptions. And one of the assumptions is that the inductor current and capacitor voltage ripples are negligible. So if you see the inductor current in CCM, it will have some ripple. So it has some average, and then on that average, it has some uh, AC component, or what is called the ripple. So it goes from some minimum value to some maximum value. And when we do the steady state analysis, we will assume that this ripple is very small, so that I can just say the inductor current is equal to an average value. So that average value will be just in between this waveform, and I will just, when I do the analysis, I will take the average value instead of uh, the ripple. Similarly, for capacitor voltage, I will take the average value of the capacitor voltage, even though the capacitor voltage will have some ripple. So the capacitor voltage will have some minimum, and then it will go to a maximum, and then again come back to the minimum point. Okay, so let's take an example of the buck boost converter, because here we will be able to take both of these equations. So I want to find out what is the expression of the output voltage in terms of the duty ratio, D, and the input voltage. So before that, uh, I will label my diagram. So I have a diagram with, again, the input voltage, output, resistive load or some other load, yeah, I have a capacitor C, L, and two switches. So, so I am defining a convention. So the plus minus basically I have defined for the input voltage, the inductor, capacitor, and output voltage. So these are my conventions, and I've also defined the current conventions. So these conventions mean that if the current is in this direction, for example, for the inductor, if the current is from top to bottom, then I will take the current as positive. If the current is from bottom to top, then I will take it as I will consider that current as negative. Similarly, for the capacitor and the output voltage, if the current is from top to bottom, I will take those currents as positive, and if the currents are from bottom to top, I will take those currents as negative. Similarly, for the voltages as well, I've defined the positive convention of voltage. So if the top terminal is at a higher potential than the bottom terminal, then I will take it as positive voltage. And if the top terminal it is at a negative at a less potential than the bottom terminal, then I will call it as a negative voltage. So these are my conventions. And finally, the S1 switch, I've defined the duty ratio in terms of the S1 switch. So the ratio of the on time of this switch divided by the uh, total time, the on time plus off time, that is the duty ratio. And I'm taking the switching frequency as constant. So this 0 to TS will be periodic, it will be repeated. So now I can basically divide my time into two sections. So one section is from 0 to DTS. So DTS is just the on time, right? If I want to find out T on, I will just, so that will just be equal to D into the time TS. So from 0 to DTS time, I will have one circuit because S1 will be on and the other switch will be off. And from DTS to TS, I will have another circuit because S1 will be off and the other switch will be on. So let's just see what those circuits will look like. So on the left, I have the how the circuit will look like during 0 to DTS time. So this S1 switch will be on and the other switch will be off. So the inductor will basically be connected to the input voltage. So the voltage across the inductor VL will be equal to Vin. So so in each interval I want to find two things. I want to find the voltage across the inductor and I want to find the current through the capacitor. So for 0 to DTS interval, the voltage across the inductor is Vin and the current through the capacitor is minus I out. So I hope you can understand this because of the way I have defined these two currents. Because in this duration, the current that is flowing through IC. So if I just use KCL at this node, I will find out that IC plus I out is equal to 0. So IC is equal to minus I out. Okay, so that's the I guess simplest way to understand that IC is equal to minus I out in this interval. And in the next interval from DTS to TS time, I can see that my inductor voltage is equal to the output voltage and the capacitor current. Again, if I just use KCL at this node at the top of the converter of the circuit, I will find that IC current is equal to minus IL minus out my out. Sorry, minus IL minus I out. So here I have taken those two assumptions that I mentioned. So I have considered, so the V out voltage is basically the voltage across this capacitor, and I have taken that as, and I've neglected the ripple across that voltage, and I've taken it as an average value of V out. Similarly, I've taken the current through the inductor as IL, which is the average value of this current, inductor current. So these are my equations for these two intervals. For 0 to Ts interval on the left, I have the inductor voltage and capacitor current, and on the right, I have the inductor voltage and capacitor current for dTs to Ts interval. So now I will use my voltage volt second balance equation and current or charge balance equation, and I will find out the average voltage, uh, average output voltage and average inductor current. So if I use the inductor volt second balance equation, so the integral of the voltage across the inductor from 0 to Ts should be 0. So in dTs interval, the voltage across the inductor is Vin. Then I add the voltage across the inductor during 1 minus dTs interval, because this interval is just dTs to Ts, which is 1 minus dTs. And this whole sum is equal to 0. And then if I rearrange these, I will find out that V out is equal to duty ratio divided by 1 minus duty ratio times input voltage and a minus sign. So that means if I have a positive input voltage, using this convention, if I have a positive input voltage and the duty ratio can only be positive, then I will get a negative output voltage. That means the top terminal will be at a lower potential compared to the bottom terminal. So this is the equation for the output voltage. And similarly, using the capacitor charge balance equation, I can find out that the inductor current average will be 1 by 1 minus d times the output current, again in uh, a negative sign is there. So because the output voltage is basically positive, so the bottom terminal is positive, so current will flow from bottom to top, and that current is negative based on the convention that I have defined. So the inductor current will just be minus of the output current based on this convention that I have defined here. So this way you can see the how the voltage polarities will come and how the equations will come. And you can also see that if you use different, so the duty ratio can vary from 0 to 1, and if you substitute different values of duty ratio in this equation, you will find out that the output voltage can be less than the input voltage, and it can also be more than the input voltage. So that is why this kind of a converter is called a buck boost converter. So buck means I am stepping down the voltage, so the output voltage will be less than the input voltage, and boosting means I'm stepping up the output voltage. And since this converter is able to do both, it can uh, get step down and as well as step up. That is why it is called a buck boost converter. So this is an example of how do you analyze these converters and how do you use the basic concepts of the inductor equations, the capacitor equations, and the periodicity of these waveforms to arrive at the different voltages and currents. So this was just a brief introduction. Further, you can do a lot of things. You can then find out what will be the voltages and currents through these switches. And based on the polarities of these voltages and currents through the devices, you can see whether the switch that you require is a one quadrant switch, two quadrant switch, and in which quadrant does it lie. And based on that, you can select a diode, whether a diode is sufficient or whether a some other kind of device you would be needing. So that is the switch analysis you can do, and then you can also uh, find out what will be the ripple current and ripple voltage in the capacitor and inductors. So a number of things you can do, and then you can also find when this kind of a converter with a which does not have bidirectional switches, which has a diode and some other switch, when that converter will go into CCM and when that converter will go into DCM. And you will find that it depends on the inductor value, it depends on the input voltage, and it depends on the output current or the average output current. So that those things you can uh, do later on. So for this subject, I will suggest you can consult uh, Fundamentals of Power Electronics by Robert Erickson and Dragan Maximovich. So this is one of the recommended books in the course. So if you go to the first week lectures, uh, the the online lectures, NPTEL lectures, and at the end of the first week, you will find that this is one of the books that is recommended. I believe this is one of the books, and the other book is Power Electronics by Ned Mohan that I also mentioned in the last week. So there you will find a lot of good information about DC-DC non-isolated converters. So now let's just move on to the problem solving session. So I will talk about the uh, power factor correction during the course of the problem solving, but I unfortunately did not get time to prepare some slides for the PWM rectifiers. And I understand that's an important concept, and maybe if time permits in the next week, I'll try to include some slides for that. So for now, let's just begin with the problem solving. So, so here I'll talk about the current limit control. So the question is the average value of the output voltage for non-isolated DC-DC converters is controlled by current limit control, and this control is only possible in which type of a load? And the options are inductive, capacitive, resistive, or it can be either inductive or capacitive. So these are the four options. So I will just go to the, okay, let me just talk about, okay, some of the students uh, are offering their answers, and let's just see what happens. So, so here I have a buck converter type of circuit, even though I don't have the inductor and capacitor. I have the inductor as the load. So this is the main switch, and the other switch is a freewheeling diode. And you can see when this switch is on, the input voltage will come across my load. And since it is an inductive load, because I'm applying a positive voltage across my load and the load is inductive, the inductor current through the load will rise. So the output current will basically rise. And the current limit control basically says that when this load current reaches some maximum point, which we have defined as Imax, we will then turn off the this switch, and then the other switch, the freewheeling diode, will just turn on. And during the freewheeling diode, you can see then the inductor will not have a positive voltage. In fact, if the inductor current is like this, uh, it will have a negative voltage across the inductor, and the inductor current will drop. And once it reaches a negative point, a minimum point, which we have defined as I minimum, we will again turn on the S switch, and the freewheeling diode will basically turn off. So in current limit control, what we do is we turn off the switch and turn it off based on whether the load current is, uh, when it touches I max, we will turn off the switch, and when it goes to I minimum, we will turn it on again. And so the condition for this happening is that in the on time, the inductor current should rise in a gradual manner. So number one, it should rise, and number two, it should rise in a gradual manner. Because if it rises in a sudden manner, then we will not have any time, any t on time. It will just, we will turn it on, and if for example the output current rises suddenly, and it will reach Imax, we will have to turn the switch off. And if that is the case, it will again fall down to I minimum. So in that case, we will not the current the control will not work. So the control will only work uh, if the uh, if the output current rises and falls, and it rises and falls in a gradual manner. And then you can see that that can only happen for an inductive load. Because of the inductor equation, the L di dt is equal to the uh, the voltage across the inductor, you can understand that because we cannot have infinite voltages, the di dt will always be finite. So that means the change in the inductor current will always be finite. And since we have the inductor is basically part of the load, so that is why the load current cannot change suddenly. So this kind of a situation can only happen for an inductive load. So just to see this further, you can now see what will happen in resistive load case. So here I have a resistive load, and when the switch is on, so I am again showing the Imax Imin, but you will see that these currents are not making any difference. So if I have the switch on for some time, that means input voltage will come across the resistor, and since it is only a resistor, the output current will be input voltage divided by the resistance. So V in by R, it will be uh, this current will be at that point. And since V in is constant and the resistance is constant, this current will also be constant. So it will not rise or fall in any manner. So it will not reach Imax, it will not reach Imin. So we cannot use current limit control to turn off this switch or turn it on. And when this switch, if we turn it off in some other way, then the just suddenly the voltage across the resistance will go down. And since it is a purely resistive load, the current through it will also go to zero. So in a resistive load case, we will have the load current in like the way I've shown. It will just be some pulses. And so you can understand we cannot use the Imax and Imin to control this switch. So for resistive load, we cannot control the uh, the converter in a current limit control fashion. So similarly, you can also see if you will just you can try on your own what will happen for a capacitive load, because the capacitor voltage cannot rise or fall suddenly, but the capacitor current can rise or fall suddenly. So that is why we will again not be able to use the current limit control. So that is why the answer to this question is that the current limit control strategy, this can only be used for an inductive type of a load. So I hope that is clear. So if anybody has any doubts or any questions, just you can write in the chat. So the second question is, which of the following techniques helps to improve the power factor? So those of you who have uh, studied the course lectures, you can just uh, mention your guesses. What do you think? Which of these will improve the power factor? Okay, I guess uh, it is known that all three of them will improve the power factor. So let me just talk about how they are improving the power factor. So let me consider the case of a single phase fully controlled converter with a freewheeling diode. So, and let us consider a load which takes a constant current, a highly inductive load. So in normal operation that we have studied previously, we will have some angle alpha after which we will give the pulses to the thyristors, and then we will get a voltage across the load, and then it will continue up to pi, and because of the freewheeling diode it will go to zero, the voltage, output voltage, and then again after some pi plus alpha angle we will turn it on again, and this will continue, and the source current will look like this on the that I've shown in blue. So it is basically the angle between the source voltage Vs and the fundamental of the source current is alpha by 2. So it is the source current is the fundamental of the source current is lagging the fundamental source voltage by alpha by 2. So it has low displacement factor because of this alpha angle. So if I increase the alpha angle, the displacement factor will increase. And again, the displacement factor is the cosine of the angle between the fundamental of the voltage and the fundamental of the current, source current. So because of this alpha angle, the displacement factor is low, and power factor is again also low because displacement factor comes into the power factor as well. And in this case, the current is lagging the voltage. So this is for normal operation. Okay, Girish, do you have a question? Okay, displacement factor is the cosine of this angle that I mentioned. The angle between the fundamental of the voltage, which here is Vs in gray, and the fundamental of the current, which is Is1 dashed. The cosine of the angle between them, which will be alpha by 2 in this case, that is the displacement factor. And the power factor will be the RMS of the fundamental current divided by RMS of the actual source current, which is this quasi-square wave, times the displacement factor. So okay, let me just write here. So displacement factor is cosine of, let me write phi. Phi is the angle. And the power factor is, first of all, it is Is1, which is the RMS of the fundamental of the source current, divided by Is, which is RMS of the actual current, so the actual square wave, times the cos phi. Okay, I hope that is clear. Yes, there is slight difference between them. I guess when you are considering the reactive power, you just go by the definition of the reactive power. So that will be the RMS voltages times the sine of the angle. And similarly, the reactive power will be the RMS voltages, the product of the RMS voltages uh, times the cosine of that angle. Okay, so the point here is that for the normal operation, we will have a lagging current, and that will be by alpha by 2. And so the cos phi will be less than 1, and this is1 divided by is will also not be very high. So this will also be quite low in this case. So this is for normal operation. Now we can come to the extension angle control. So here what we do is we turn on the thyristor. It has to be a GTO because we want, so we will need a turn off control as well. So we will turn it off. If we turn it on at zero angle, and we will turn it off at some angle which is pi minus beta. Okay, and again this will continue for the next half cycle as well. So if you see, the source current in this case will be will have some lead angle. So instead of lagging, it will be leading by this angle beta by 2. So this we can basically use because most of the loads that we have, those are lagging loads. So if we then can simulate a leading load because a capacitive load is a leading load, using this kind of a control, we can simulate a uh, leading load or a capacitive load, and if it is added to some other uh, lagging load, then the power factor can improve. So you can just assume that if this source has some multiple loads, one of the load is this converter, and another load is some other lagging load, and this converter is drawing a leading current, that other load will be drawing a lagging current, and the sum of those two will be basically an improved power factor compared to the original case. So this is for extinction angle control. And the point to here, what is to be noted here is that we are deliberately turning the device off, even though it is still being forward biased. So that is why we need a device which is able to turn off, which we have control turn off functionality. So the normal thyristor will not work. We have to use a GTO or some other device like a IGBT, BJT, or MOSFET. So this was extinction angle control. So I hope it is clear what improvement or what advantage this will have. So another way to that was in the question is symmetrical angle control. So here what we do is we turn on uh, the thyristors or the GTO after some time, and then we'll turn it off at a particular time. And and this angle, so from 0 to turn on, has to be equal to from pi to turn off. That is when we will call it a symmetrical angle control. And if these angles are equal, that is 0 to the turn on and the turn off to pi. So if these two angles are equal, then you can see the current will look like this, and the fundamental of the current will be exactly in phase with the fundamental of the voltage. So in that case, we will have a high displacement vector. So ideally, the displacement vector will be 1. So because the angle between them is 0 and cos phi, cos 0 will be 1. So in this case, we will get a higher displacement factor, and we can see for the same output voltage, we can get a higher displacement factor and then a higher power factor as well. And so on the top, I have shown how do we basically get for how much time should the devices be on. So we have a carrier waveform. So this triangular waveform is a carrier, and as you can see, it has a switching frequency which is twice the supply frequency. So the supply frequency is Vs from 0 to 2 pi, and this triangular waveform is basically at twice this frequency. And then we have a reference voltage, reference waveform, which is this straight line, horizontal line. And when this reference touches when it is greater than the carrier waveform, I will turn on the devices. And when it's less than the carrier waveform, I will turn off the devices. So this is how you can understand how this how these switches are being controlled. But so even though the displacement factor is quite high here, but what we can note here is that this kind of a quasi square wave, it will have lower order harmonics as well. So it will have a fundamental, and then it will not have a second harmonic because it has half wave symmetry. You can consult later on what half wave symmetry is. But that basically means it will not have any even harmonics, but it will have a third harmonic, it will have a fifth harmonic, and the lower order harmonics. So the lower order harmonics means these which are closer to the fundamental. So the third harmonic, fifth harmonic, and seventh harmonic, and so on. While the higher order harmonics will be which are at a much higher frequency than the fundamental. So in this kind of a current, we have significant amplitude of lower order harmonics. And the problem with having lower order harmonics is that it is difficult to filter them out compared to higher order harmonics. Because when we have a filter, for example, an inductive filter, the impedance of that inductive filter depends on the frequency of the current. So if the current is at a higher frequency, the omega L, which is the impedance of that inductor, will be higher because omega is high. But for lower order harmonics, because omega is smaller, the impedance of the inductor will also be smaller. So that is why we want to have we want to reduce or eliminate the lower order harmonics, even if we increase the higher order harmonics, because it is easier to filter out the higher order harmonics using the general passive loads like the inductor or capacitor. So now we can come to a PWM control or a pulse width modulated control, in which we will see that the lower order harmonics are reduced and we have higher order harmonics. So, so you can see now if we want to have an average voltage, we can do it by, uh, we want to have an average output voltage, we can do it by constantly turning the switch on and off. So if we turn it off for some time and then off again, on for some short duration and again off, and this on time if for all these pulses is same, so that is the normal pulse width modulation control. The on time of all these pulses is same as, which is I've given as delta m. In that case we will have a voltage which has this kind of a waveform. The pulse width of all these pulses is same, and the current will have a similar waveform to the voltage, but it will have a constant amplitude because the load is drawing a constant current. And then you can see that the lower order harmonics will be reduced or eliminated from this because the waveform is has all these pulses. And if you do the analysis, you can find out by different on time and off time, we can selectively eliminate different harmonics. But in general, in this kind of a wave, the lower order harmonics will be less compared to the higher order harmonics. So this will not only improve the THD, but it will also improve the power factor as well, because the fundamental in this case will be closer to the RMS of the actual waveform. And on the top, I have shown how we can get this kind of a waveform. So in the previous, we had the carrier had a frequency which is twice the frequency of the source supply. But in this case, the carrier has a much higher frequency. So here I have shown which is, I think, 8 times the source frequency, but it can be even higher. In general, it is much higher than the source frequency. But just to show how it works, and then again we can have a reference waveform, and then we can use some logic. For example, here I have used the logic when the reference is higher than the carrier. The carrier is the triangular and the reference is this constant line, the horizontal line. And when the reference is higher than the carrier, I am turning on the devices so that I will get some voltage at the output. And when the reference is less than the carrier, the output voltage, I'm turning off the devices so that output voltage will be zero. So this is the logic that I have used here, and I'm getting this kind of a voltage, and the current has higher order harmonics, but lower order harmonics are reduced or eliminated. So this was normal pulse width modulation control. Then we can also have sinusoidal pulse width modulation control. So the difference here is that my reference waveform is not constant. It is not a horizontal constant, but it also varies sinusoidally. So what that gives me is that uh, the output voltage will also, the pulses will have different widths. So close to the zero angle, the pulse width will be small. And as we go to 90-degree, the pulse width will increase. And then again, as we reach pi, the pulse width will decrease. So if you see here, if you do an average in one high frequency cycle, you will see the high frequency average will also be sinusoidal. So for example, close to zero, the average here from zero to some this point is less. But later on at near pi by 2 angle, the average of this is also high. So that means this is a much closer approximation to the sinusoidal waveform. Even though it has higher order harmonics, but You can find out if you do the Fourier analysis, you will find out that the power factor is further improved in this case because we are varying the pulses in a sinusoidal fashion. So the pulse is smaller, close to 0 and pi angles, and the pulse width is greater, close to 90 degree or 270 degrees. So these were all the PFC pulse width power factor correction techniques or power factor improvement techniques. Okay, Girish, you have a question? Yes. Yeah, you can understand because if you see this waveform, it has a high frequency component, and this high frequency component is it has a larger amplitude compared to the normal square wave. You have the square wave or the quasi square wave. In that case, the fundamental will have a high amplitude. The lower order harmonics will have high amplitude, but as you go higher in the harmonic spectrum, the amplitude will reduce for the quasi square wave, a wave like this. If you can just in MATLAB or some other by hand you can do the Fourier analysis. You can see for this kind of a waveform, the amplitude of each harmonic, it will have a harmonic factor in the denominator. So it will have some it will have a direct dependence on the this amplitude of the current, some I constant or I load. It will have a direct uh, relationship with that, but it will have an inverse relation with the harmonic number. So as the harmonic number increases, the amplitude of the harmonic will reduce. So in this case, the lower order harmonics are higher compared to the higher order harmonics. But in this case, because the amplitude of the high frequency, you can see that uh, just intuitively in that sense, you can see that it is going from 0 to some high amplitude and again 0 to some high amplitude. So that is, and this is being done at a high frequency. So that is why the high frequency content is increased. But if you want a detailed explanation, you will have to do the uh, Fourier analysis of this kind of a waveform. So you will have to find the AN and the BN. So one of them will be 0 because of half wave symmetry. But if you find out, you will see that for higher orders of harmonics, the amplitude will be higher compared to the lower order harmonics. And then we can filter them out using a very smaller filter compared to lower order harmonics. So in all these cases, we can see the power factor is improved. So the answer to this question is that the power factor is improved using all of the above. Okay, so before continuing, we will again take a short break. So we'll resume at 7:15 in this case. So in the meantime, if someone is free, you can just consider this question and try to see what do you think is the answer. So I will continue at 7:15. Okay, so let's continue. So this question is asking about the pulse width modulation that we just studied. Uh, if the amplitude of the reference wave and the carrier wave are made equal, then what will be the pulse width in degrees? Okay, so some people are saying C. Okay, so it basically depends on the logic that you use for generating your pulses. So for example, in the case that I had shown previously, I had used the logic that the when reference is greater than the carrier, I will turn on the switches so that I will get a pulse. And if you see in this kind of a logic, if I just if the reference is now at equal to the amplitude of the carrier, then I will just the switch will be on for the entire time because if I take this reference to the top to the amplitude of the carrier, it will always be greater than the carrier. So in that case, it will always have this the switch will always be on. I will get a pulse from 0 degree to 180 degree, and then it will basically continue while the voltage and the current pulse will be like 0 to 180 degree, and then mm, in the negative portion from pi to 2 pi. So if for this logic that if I am turning the pulse on when the reference is greater than the carrier, then the answer will be 180 degree. However, if I had the inverse logic that I am turning the pulse on when the reference is less than the carrier, in that case, if I take the carrier to the top, then it will always the reference will basically be it will basically always be off because it will never get the chance to be less than the carrier. So I will never be able to turn on the devices and I will not get any pulse width. So the answer in that case will be 0 degree. So if you get a question like this in your assignment or in the exam, you will basically have to consider what has been taught in the course. So if you see the course in that in the lectures and in the slides, you will see that the B kind of a logic is taken, that you will get a pulse when the reference is less than the carrier. So that is why the answer to this question, and in the assignment, if you get some similar kind of a question, you should write based on what was shown in the course lectures. So the answer to that in that case will be 0 degree. So the next question is the variable frequency control of a chopper is also known as which of these? Either is it known as pulse width modulation, frequency modulation, hysteresis control, or none of these? So you can guess in the chat. Okay, so this is quite simple. That in pulse width modulation, I mentioned that. So this is basically the constant frequency control logic that where we keep the switching frequency constant. We just vary the T on T off times. In variable frequency control, we will vary the switching frequency itself while we keep the T on constant or we keep the T off constant. And that that kind of a control is also called frequency modulation. Hysteresis control is just like the current limit control, even though that will also be, it can be variable frequency. But when we talk about variable frequency system, we are mainly talking about what we mean is frequency modulation. So the answer to this question is frequency modulation. So the fifth question is a single phase full converter is made to deliver a constant load. So this is related to the last week's topics. So we are given for zero firing angle, the overlap angle is 15 degrees. Calculate the overlap angle when the firing angle is 60 degrees. So this is the single phase full conductor converter with the source inductance. So because we are given the firing angle as well as the overlap angle. So we have to understand it is a, I mean, it is already mentioned it is a full converter, but since we are given the overlap angle, we understand that there is a source inductance. So the waveform will look like this. I mean, this is the current waveform. The voltage waveform will actually it will start at this point after alpha plus mu angle, and then it will continue up to uh, the negative. It will go into the negative as well because uh, we have a constant current load when we don't have any freewheeling diode that is mentioned in the question. So anyway, now if you see this system, this is one of the equations that you can derive for this system. So in this equation, we have alpha, we have mu, and we have omega, the source inductance, uh, the supply voltage level, and the output current. But if you see the question, we are only given the alpha angle and the mu angle for one case. We are not given the other quantities. But you can also see that the other quantities, we are told that they will not change. Either we are told or we understand that they will not change. By changing alpha, we cannot change the source inductance. The supply voltage will not change. And we are told that it is a constant, it is feeding a constant load. So if we change alpha angle or mu angle, then the load current will also not change. So if we take the first case where alpha is 0 and mu angle is the overlap angle is 15 degrees, then we can find the value of this term in the right hand side of the equation. And if you substitute the values 0 and 15 degrees, you will see that this whole term is equal to 0.034. And this quantity remains constant as alpha changes. So that is the point that you have to understand in this question, that this quantity will not change as alpha changes. And we can use this fact for the other case. So in the second case, we are given a different alpha angle and we want to find the mu angle. And if we know this quantity, the value of this quantity, then using this equation, we can find out very easily. So again, I'm using a alpha of 60 degrees. Mu I have to find out, and the second term I am using same as 0.034. And if you substitute these values, you can find out that the mu angle is equal to 2.229 or 2.23 degrees. So the answer to this question is A. So the next question is, in a single phase semi-converter with resistive load and a firing angle alpha, each SCR and a freewheeling diode would conduct for, and you have all these options. So, so you have to understand here, you have a semi-converter with a resistive load and a freewheeling diode. And the question is asking about the conduction time or conduction angle of SCR and freewheeling diode. So yeah, I can give you 1 or 2 minutes because this should not take too much time. But uh, if 1 or 2 minutes, if some of you can guess what should be the answer. What you should note is the resistive load. So what would happen in case of a resistive load and the freewheeling diode? Okay, so it's an interesting question. Some of you are answering C and some are answering D. So, okay, let's look into this question. So this is a converter, and so we have an alpha angle. After an alpha angle, we will give the pulse to T1. So T1, D1 will conduct, and we will get this kind of a voltage at the output. But because of the freewheeling diode, we cannot get a negative voltage. However, for a resistive load, the freewheeling diode is not important, or it will not play any role, because the current waveform will just, if you see the output current waveform, it will just follow the output voltage waveform. And when the output voltage goes to zero, the output current will also go to zero. So after that, we don't have any current in the load. So the freewheeling diode, there is no current to be freewheeled. So the freewheeling diode with a resistive load will not conduct at all. The freewheeling diode only conducts in case of a inductive load. So if you see here uh, the SCR, the T1 or T2, it will conduct from alpha to pi, and the other SCR will conduct from pi plus alpha to 2 pi. So in each case, it will be the duration will be pi minus alpha, but the freewheeling diode will not conduct at all. So the answer to this question is D, pi minus alpha for the SCR, and the freewheeling diode will not conduct at all. So 0 for freewheeling diode. And what is to be noted here is that this is only the case for a resistive load. If we had an inductive load, then we would have some extinguishing angle or some other angle beta for which the freewheeling diode will conduct. So the next question is, in a three-phase, three-pulse M3 type controlled converter. So we have a three-phase, uh, three-pulse converter. M3 type means it's a three-phase half-wave control, fully controlled converter. So we have three thyristors, T1, T2, and T3. So the question says that T1 starts to conduct after an angle of 30 degree plus n degrees. At what angles do T2 and T3 start to conduct? So assume that the conduction sequence is T1, T2, T3. So that means T1 is connected to the A phase, T2 is connected to B phase, and T3 is connected to C phase. And you are given that T1 starts to conduct at 30 degrees plus n degrees. So 30 degree from the A phase voltage zero crossing. So it is 30 degree plus n degree, n will be the firing angle. So the question is asking at what angles do T2 and T3 start to conduct. So again, you can take 1 or 2 minutes. You can maybe draw this circuit one and draw the three phase voltages, and then you can just try to see when do you think these T2 and T3 will conduct. Okay, so most of you has guessed correctly. So let's just see how it happens. So we have this three-phase half-wave controlled rectifier, and this will be the voltages. The in gray you can see the actual three-phase voltages, and again these are in common cathode configuration. So when the anode voltage is highest, at that time is the point of natural commutation, and after that point we will have some angle alpha, or actually in this case it is n degrees. So after that time, the thyristor will conduct. So 0 plus alpha angle or n angle, T1 will conduct. And if you see for T2, the natural commutation point is when the B voltage becomes highest, which happens at 150 degrees. And for this T3, the natural commutation angle happens at 270 degrees when VC becomes the highest. And after that, some angle alpha or n degrees, these T2 and T3 will conduct. So the answer you have, as you have guessed, is 150 degree plus n degrees and 270 degrees plus n degrees for T2 and T3 respectively. So the eighth question is, in case of a constant frequency system, T on is given as 1/4 of the switching time, total switching time, which is T. If the chopping frequency is 2 kilohertz, find the value of T off. So again, this is not very difficult question. You can try in 1 or 2 minutes. You can probably find the answer. So we have a constant frequency system. And T on is given, you have to find T off, and the switching frequency is also given. So someone is saying 1, or A. A is the answer. Okay, so we are getting answers A and B. I'll wait 1 more minute just to see if other people can also try to find. Okay, so the T off will be just the total time T, the switching time T minus T on. And the switching time we can find as the inverse of the switching frequency, which is 2 kilohertz or 2000. So the switching time or total time is 1 by 2000 seconds. T on is given as 1/4 of the total time. So it will be 1 by 8000 of a second. And then you can just find out T off, which will be just T minus T on, which is T minus T by 4, which is 3 by 4 of the total time. So uh, 3/8 of a millisecond. Okay, so the answer is B. So, so if someone needs these slides, you will find these in the Google folder. So, in the ninth question is asking, in the current limit control method, the chopper is switched off when, and the options are when the load current reaches the lower limit or the upper limit, whether load current falls to zero or none of the above. So this we actually studied in the first question. Okay. Okay, so someone is, most are saying B, but someone is also saying A. So let's just clarify it. So if we have a chopper like this, even in the boost chopper case, you will again have the inductor current will rise when the main switch is turned on. So so the question is asking, when will we turn off the chopper switch? So we will turn it off when it reaches the Imax value, when it reaches the maximum value. At that point, we will turn it off. So you can see for a buck type chopper or a step down chopper, when I turn the S switch on, then I get a positive voltage across my load and the inductor current will rise. And when it reaches the Imax, I will then turn it off. Then the current will freewheel and the current will drop. So I will turn the switch on at I minimum and I will turn it off at I maximum. So the answer to this is the load current reaches the upper limit. At that point, this chopper or the switch will be turned off. Okay, Girish, you have a question? So what was taught in the course, I think it was just that if we have a thyristor in the as the yeah. So if we have a thyristor as the main switch, then we call it a chopper. Uh, and basically we will use thyristor only in case of high power applications, because in low power applications thyristor very is not recommended, because the switching frequency is limited. We cannot go to very high switching frequencies, and that means the filter L and C components will be quite large. So that is, yeah, yes. Yeah, yeah. So in that case, you will get two. So for example, if you have this kind of a situation, but an E is included here, right? So you will have two circuits. One circuit will be when the switch is on, the other circuit will be when the switch is off. And in both these cases, you will have a differential equation for the current. So the current will be, so actually this is done, I think, in the last lecture of this week for buck converter. It has been done for an RLE load, if I remember correctly. So you will get a differential equation uh, using the in the for the load current for the yeah. So if you so based on the differential equations, you can find the actual value of uh, the current, and based on that, you can also find the voltage across the because the voltage across the resistor will just be resistor times the current, and the voltage across the inductor will be the difference derivative of that voltage times the L, right? So can you repeat? I didn't get the question exactly. Okay, so yeah, but in this case, in this kind of a chopper circuit, you don't really need that inductor because the load itself is inductive. So we will just take the inductance of the load itself. So in RLE DC motor kind of a load, we don't need a inductor and then a capacitor and then we will have the load. So in case if we had that case, then we can use the inductor volt second balance. But in this case, you will have to use the differential equation. You can find the value of uh, the expression for the load current, and then basically, yeah, the voltage you can find the resistor voltage is quite simple. The inductor voltage will be just derivative of that inductor current. Yeah. Okay. So this was the ninth question. The final question is we have a step up chopper. And so again, the step up chopper will be a boost converter, but here we will have thyristor as the main switch. So the input voltage is 220 volt and the output voltage is 660 volts. If the conducting time of the thyristor is 100 microseconds, then what will be the pulse width of the output voltage? So, okay, let's see. So again, so here we are assuming we don't have a capacitor at the output. So that is the only way we will have a pulsed output voltage. So we have an inductor at the input side, and then we have the chopper switch, the thyristor, and a freewheeling diode. When the thyristor is on, uh, the inductor will store energy. The inductor current will rise. The inductor voltage, the voltage across the inductor will be V in, and the current will rise. So that is the energy storing time. And during the T off time, that energy will be fed to the load. So during the T on time, so here we don't have any capacitor at the output. We don't have a constant output voltage. So here the output will just be disconnected. The output voltage will be, let's say, zero in this case. And in T off time, we will get some output voltage because the inductor will feed to the load. And so basically, the question is asking what will be the pulse time of the output voltage. So the question is basically asking for the T off time. So you're given the input voltage, you are given the output voltage. The input voltage is 220 volts, the output voltage is 660 volts, and you are given the thyristor on time. So you are given the T on time. So you are asked to find the T off time. Okay, so let me wait for a few minutes if some of you can try this question. So it will not, it's not that complicated, so it will maybe take a few minutes. And since it's the last question, we can have a few minutes. So basically, you have to find the off time of the switch. You are given the on time, you are given the input and output voltages, and you are told that it is a step up chopper or a boost converter. So if you know the output voltage of the boost converter, you should be able to find. So someone is saying C, 30 microseconds. Anyone else? Okay, some people are saying C and some are saying A. So let's see. So for a chopper, the output voltage is given by the this top equation. The output voltage is input voltage divided by 1 minus D, where D is the duty ratio. It's T on divided by the total time. So from the first equation, I can find the what will be D if we are given an input voltage and an output voltage. What will be the duty ratio? And in this case, the duty ratio, if you substitute the values, you will get a 2 by 3. So two-thirds. So that basically means the switch is on for two-thirds of the total time, and you are given the on time. So the off time will be the other one-third of the time. So so you can just easily find that T off is T minus T on, and T you can find has T on divided by D from this equation, and you will basically get that T off is 50 microseconds. So the answer is A. So so these were the problems for today. So if anybody has any other questions, we can get some questions. Yeah, so like I said, I did not get time to prepare some slides. So these questions are actually from the last year's or last semester's course, this Advanced Power Electronics Convert and Control. So in that, for week 4, there were no questions on PWM rectifier. Okay, so if there is some question in the next week, we can then cover it. Or if we get some time. Okay, so I will try in the next week. I'll try some basic concepts. Yeah, so if you know, most of the content that is taught in the course has been taken from uh, Fundamentals of Power Electronics by Robert Erickson. So you can find that book online as well if you want. And so it has a chapter on PWM rectifiers very late in the book. So there you can find all. So because in the course this was taught very quickly, it was we did not get time to go into the details. So if you want to study it very carefully, you can consult that book, Fundamentals of Power Electronics by Robert Erickson. So that is Erickson. So the reason we do this DQ transform is because when we okay, there are a bunch of concepts here. So the first concept is the when we have a controller, we like to use a PI controller. The PI controller is the simplest kind of a controller, and in a PI controller works best with a DC error signal or a DC reference. So that means for a DC reference or a DC error, the PI controller can minimize the error. It can give you a zero error. So the PI controller works best for DC waveforms. But now in AC systems, like a three-phase system or even single-phase system, the waveforms are varying sinusoidally. So if we use a PI controller, the steady state error will not be zero because the waveform is varying sinusoidally. So when we use DQ, uh, what is it called? DQ reference changes. Yeah, yeah, reference transformation. So if that angle is basically, if you, if that angle is synchronized with the sinusoidal waveforms, then the DQ voltages or DQ currents will be constant. They will be DC currents or voltages. And then we can use PI controllers to control those currents. And so that is in power electronics. So uh, in drives, it is used to for vector control and some other aspects. In power electronics, it is also used for three-phase systems where we want to feed a particular power. So uh, if you have a power reference, so you want to feed a particular active power. So if you use this DQ transformation in a certain way, then your ID will correspond to the active power and IQ will correspond to the reactive power. And then by uh, giving a particular reference to the IQ or ID, you can control the active power and the reactive power that you are feeding. So, so I understand it's a very complicated concept. So if you have some in the power electronics, I am not sure because I have not. Uh, so this is not my area. So I work on a motor control. So I have done this APC to DQ for. Okay, so let me check this for what would be a good resource for uh, this transformation in power electronics, and I can mention it in the next week session. Yeah, so I will look in for, so because I have not studied this topic in detail, I will consult some books and I will see what is the uh, where in which book or in some video where it would have been uh, taught very nicely. Then I will in the next week I will suggest to you. Okay, so if anyone else has a question, okay, so if other people don't have any questions, uh, then we can leave. So I will stay here for a few minutes. So those who are have a question or they are typing, they can type. Others who have some work or they want to leave, you're free to leave. Okay, so everybody is welcome and thank you for joining. Okay. Yeah, yeah. Yes, so okay, okay. The issue is that since it's an advanced course, it is assumed that you know some of the basics. So you know what is a how DC-DC converters work, how control works, and then you will treat the advanced topics like P-terminal rectifiers, power factor correction. So that is why in the course these topics are not taught very deeply. But I will try to include some of these control aspects and the P-terminal rectifier in the next week. Okay, okay. Yes, Newton, you have a question? Okay, so I talked about the three basic non-isolated converters, like the buck converter, the boost converter, and the buck boost converter. So I'm talking about the structure of these converters. And so they have the input DC voltage, the output DC, and we usually have a output capacitor. Then internally we have these three terminals. So the input terminal, the output terminal, and one terminal connected to the ground or the negative point. And in between them, we can connect two switches and an inductor in three different ways. And those three different ways will give us three different converters. So, so one way is a buck converter where the inductor is connected to the load side. Another way is a boost converter where the inductor is on the source side. And for a buck boost converter, the inductor is connected to the ground terminal or the bottom rail, basically. So it is not necessarily grounded, but the bottom rail. So these are the structures of these converters. So next I talked about the different control strategies. So current limit control, I explained in the first problem. In that basically we have some current limits, and based on when we hit those current limits, we will turn on the main device or turn it off. So that is current limit control. In time ratio control, we can have two options. One is a constant frequency control. So the switching frequency is basically uh, the time between when we turn on the time between two successive turn-ons of the switch. So for example, here at 0, I'm turning on a switch, and then after some time, I'm turning on the switch again. So this time is the switching time, and the inverse of that will be the switching frequency. If this switching frequency remains constant while I want to change the output voltage, then this kind of a control is called constant frequency control. So this is done by changing the duty ratio. So I can change the duty ratio by increasing. So if I want to increase the duty ratio, I will increase T on time and I will decrease T off time so that my overall TS time or switching time remains constant. So this is constant frequency control. The advantage of this kind of a control is the harmonics or in the filters will be at one frequency or the switching frequency. For variable frequency control, one option is to have constant T on time. So for example, here on the top and bottom, you can see the T on time is constant. But since I want to control the voltage, for example, if I want to increase the duty ratio and I have the T on time is constant, the only way I can do that is by reducing the T off time. And by doing that, I'm increasing the switching frequency as well. So you can see in the bottom case, the T on first is the switching is turning on here and then at this point, which is closer compared to the top diagram. So that means the switching frequency is increasing. So in variable frequency control, our switching frequency will not be constant. And as we change the voltages or currents, our switching frequency will also change. Okay, so somebody is asking about isolated and non-isolated converters. I think we'll touch that in the next week lecture. So I'll talk about the applications of isolated and non-isolated converters. Here I'm just talking about the functional aspects. So then the another thing I was talking about is CCM and DCM. So constant conduction mode and discontinuous conduction mode. In constant conduction mode, basically the inductor current remains positive. It will the inductor always has some current passing through it. In DCM, the inductor current goes to zero and then it will stay at zero for some time. And the DCM happens because our devices cannot conduct bidirectional current. So because in most cases you will see the falling of inductor current is carried by a diode, and the diode can only conduct positive current. So if the current goes to zero, had it continued in this direction, it will go to negative. But since we have a diode, the current cannot go negative. That is why we have a discontinuous conduction mode. If we had a bidirectional switch instead of a diode, the current would have continued in the negative direction. So in that case, we will not have DCM, we will have CCM continuously. Even though the current is negative, we will still have DCM. Sorry, CCM. So then I talked about the steady state analysis, and the basic concept here is that in steady state, the currents and voltages will be periodic. So after every TS, we will get the same current or same voltage. So if we use the inductor, basic inductor equation, basic capacitor equation, and in the we just rearrange them, and we will find that the volt second, uh, uh, the integral of the inductor voltage will be zero, because at steady state, if we have certain positive voltage across the inductor, we should have the same area of negative voltage, so that the current through it will reach the same point, so that the overall inductor area will be zero. Similarly, for capacitor, the charge balance should happen so that there should be no excess charge, because if there is an excess charge, the capacitor voltage will rise or fall. But since we are saying that at steady state, the voltages and current reach the same value, so the voltage and current will be after every TS point, they will be same. So the inductor voltage is balanced, inductor voltage volt second is balanced, and capacitor charge is balanced. So then I talked about an example of a buck boost converter. And so this is a basic example you can see in DTS interval and uh, in the 1 minus DTS interval, what will happen to the inductor voltage and the capacitor current. And then based on the uh, inductor volt second balance and capacitor charge balance, you can find out the output voltage and the inductor current. So if you are still need some more information, you can consult the book, or this lecture will be uploaded on YouTube, so you can see the first few minutes of that lecture. So you will get more detailed explanation of these slides. I'm not able to uh, hear you clearly. So you can either talk louder or you can write in the chat because there I can read your question. So in DC-DC converter, the frequency is basically uh, the how fast the switch, how fast the transistor or the thyristor is switching. So basically this time, so if we have the switch S1, it is on for a certain time and then it turns off and then it will continue. This thing will happen periodically. It will again turn on, turn off. So the total time, so the time between one turn off and another turn on, one turn on and another turn on is the switching time, and the inverse of that is the switching frequency. And switching frequency is basically if we have a higher switching frequency, then the then that can be filtered out easily using smaller filters. So that is why we try to have as high switching frequency as possible. But the problem with high switching frequency is that the switching losses increase. So is that what you were asking, or are you asking something else? Okay, so in DC-DC converter, the switching frequency is basically how fast the devices are turning on and off. Okay, so that was it for today. I'll see you guys in the next week. Okay, goodbye.